Okay, so Assalamu alaikum wa rahmatullahi wa barakatuh once again. We are going to start directly our lecture. In the last classes, we have discussed the combined foundation. We have learned how to do one-way and two-way shear calculation as well. Okay. Today, whatever I'm going to show you, I'm going to show you how we are going to do foundation design, whether it's an isolated or combined, using different softwares. Okay, and then we'll go directly to the column chapter. Okay, and by the way, I have already uploaded your assignment for you. Your assignment is going to be an individual assignment where you need to try it yourself and submit it before 14th of December, which is going to be a good practice for your final examination. Okay. Now, related to your isolated and combined foundation samples. So, for example, if we go and try to solve this particular question, now it says a 400 mm square column. We have solved this question. Okay, and we want to try to solve it using an Excel. Okay, so we'll go to the Excel directly. This is my Excel, where there are certain inputs that you need to do. So grade of concrete, grade of steel, density of concrete, bearing pressure, or the safe bearing pressure. So safe bearing capacity is 170. Size of aggregate, the cover is how much. Grades, also factor of safety for the steel and for concrete. Length and width of the bases. So how much is the length and the width? It's not shown, but anyhow, if you input the loading, then it will give you the suggested cross section here. Okay, so the size of the column is 400 into 400. The depth we have used as 550 overall depth. So we are going to write it as 550. Okay. Remaining is a loading. So we have an axial load, which is a dead of 1050 and a life load of 300. We don't have MX because it's concentric. So it says for you here. Okay, it says for you here that according to the given loading, the suitable cross section is 2915. For us, I think we have used 3 meter into 3 meter, which is fine. Okay. Now, what you need to understand, you can see here ground bearing pressure, and the efficiency is 90%. As close as you go to the requirement, your efficiency is going to be higher. So, for example, if we keep it now 2,800 to 2,800, you will see that it exceeds 100. It means that it's failing in ground pressure. Okay, it fails in ground pressure. Why it fails in ground pressure? If we go and divide the loading into this particular area, it will give you something higher than 170. Okay, so once again, according to the given data, it says for you how much is the approximate area to be used. Okay, so let us see. So according to that, you will see whether your design is safe or not. If your design is not exceeding 100% anywhere here, it means that your design is safe. Ground pressure is related to service pressure. Checking the service pressure, if you remember. Bending is the requirement for the area or AS. Okay. Now here, in terms of moment of X, moment of Y, or area X, area Y, here we have shear, one-way shear for X, one-way shear for Y, and then we have bunching shear, which is two-way. Okay. Now eventually you will get your values here. Okay, eventually you will be getting your values here. Now, if you see, they have got a value of 549.3. Now let us see how much we have got in our scenario. We have got 183.09, and this was for 1 meter. Okay, this was for 1 meter. Okay, this was for 1 meter. Now, if you are taking width, of 3 meter, then we have this value, which is 183.09 multiplied by 3, which is going to give you 549, which is exactly the same value you have got here. Okay, so this mx, you need to understand the Excel. The Excel is giving you B for 3 meter, while we have used for the isolated to be 1 meter. Okay, calculation of D, how much is the provided reinforcement. The same thing goes for the shear, beam shear or one-way shear, if you remember I have told you. And then we have bunching shear as well. And then it's going to be compared with the final VC at the end. Okay, so this is using Excel for an isolated. For a combined, the same process goes. Okay, where you are required now to input for 2 columns. Okay, so it's the same Excel if you see. The only thing that you have for column number 1 or column number 2, and then you have length, width, depth, the same. You have cross section for column number 1, cross section for column number 2, and then you can see here that you are having eccentricity. Now, how eccentric is the 2 columns from the center of the foundation. For example, you can see if this is 300 and I change it to 700, you will see that they will move from each other by a value of 700. Okay, if we keep this one 0, they will come, the eccentricity between them to be 0. Okay, and accordingly, you can input the value here. For example, I want this eccentricity to be 500. This eccentricity to be, for example, now it's locked. Anyhow, you can unlock it. Okay, you can unlock it and you can modify the second one. Okay. Now, for example, here it says for you after you input the eccentricities, after you input the depth, and you can see, for example, here it's failed. It says for you, you can use different sizes, either this one, that one, which one. Now you can see mainly we are failing. Mainly we are failing in ground pressure. It means that the area is not sufficient. So I'll go here. I'll choose whatever was recommended by the software. So let us say this is 3,005. Let's say 3,600 into 3,000. You can see now it's 96%, lesser than 100, so it's fine. You can see that the efficiency of the shear is very low. It means that the depth is very high. So we can go and increase. Once again, if you remember, if my depth is higher, the shear resistance is higher. Okay, so we can reduce to 500, and you can see that now that this is increasing. Okay, once again, you try to the maximum. Once again, if we increase the depth, of course, the resistance to shear is going to be higher. Okay, if I have 1 paper and I try to cut it, it's going to be easy. If I have 1,000 papers and I try to cut them, it's going to be hard. So once again, increasing the thickness is going to control your shear as well. Increasing your area is going to control your pressure, according to the concept of stress is equal to force divided by an area. Okay, so once again, if we change it to 600, you can see that the bearing capacity or the shear force, the bunching one-way and two-way shear are changing. Okay, and you will get the bending moment diagram, but the most important thing, you will get your reinforcement. Now you have things you need to understand, like for example here you have B1 and you have B2. B1 is representing, B is representing bottom, 1 is representing X, so this is a reinforcement of X, this is a reinforcement of Y. So B is for bottom, 1 is for X, 2 is for Y. In isolated we have only bottom reinforcement X and Y. In combined foundation, if you remember, I told you normally we are having top and bottom, but the problem that we have solved was only having bottom. Anyhow, here you can say B1, B2, T1, and T2. Okay, now B1 is representing, B is representing bottom, 1 is X, so this is for X, this is for Y. T is representing top, so this is top for X, this is top for Y. Now this is using Excel. Now other softwares are there, like for example Procon, where you can go and input the values for your base. So for example, if you can see here, the base length, for example, let's say it's 3 meter. You have options whether to go for column 1 or column 2, how many columns you have. So for example, we'll go for C, which is representing the first dimension of the column. Now you can see if you input only 1, it will understand that it's a circle, because circle is having 1 dimension, which is the diameter. If we input 2, it means that's a square. If we input, for example, 0.4 into 0.6, it will turn up to be a rectangle. Now, our case is 0.4. E and F is related to eccentricity. So, for example, if we go here, you will see that you are now eccentric by 0.5 meter. If this is 0, then no eccentricity. Column height, if you want to have column height or whatever we call it, stub or starter, you can keep it as 1 meter. You can see normally we have it as 1 meter. Base depth, how much we are having, it's 0.55 meter. So you can see now there is a depth for the foundation. Soil cover, how much is your soil cover, the ground level? So for example, let us keep this one to be 1.8. And now we are having 1.8 cover, which is a backfill. And you can see backfill is coming. Density, concrete density is 24. Soil density, normally we take it as 18, but that changes when normally for the soil friction angle, once again that depends on the soil investigation report. It is 33. Constant once again is around 0.5, but once again these values are depending mainly upon your soil investigation report. Rebar depth in terms of X, how much is your dx, how much is your dy. Okay, how much is your dx and how much is your dy, or how much is the cover. How much is the cover here? So 50. Okay, how much? Let's say for the y we are having it to be 60. For the y to be 60. Okay, factor of safety for the self weight. Okay, 1. And then here you can take it as 1.4, which is ultimate. Maximum safe bearing capacity 170. Overturning, you can take it as 1. Slipping, you can take it as 1 as well. FCU of the base is 35, for example. FCU of the column is 35. Grade of steel is 460. Load case 1. Column number 1. Okay. Load factor for ULS is 1.4. Here it's 150. Second loading 1.6. Then this is 3. Okay, after we finish from here, we can go for the design. You can see that this is failing here. Okay. According to the extra load that we are having because of the backfill. So for example, now we can go and keep this one to be 3.2, or you can ask the software to optimize. Optimize means it will try to choose the best length, the best width, and the best depth. So you can see now if we try to optimize, okay, you need to input the cost, so it will give you, but anyhow, let us try 3.2 to 3.2, and then going for the design. You can see still it's above 170, so it's failing. So let us keep it 3.3 and then 3. 3.3. Okay. Most of these questions are from the question here. Okay. So here you can see that these are the values. The bearing pressure now is 169, which is lesser than 170, so it's fine. And the bending moment has been calculated here. Shear one way, punching shear is calculated as well. And eventually at the end, you will be getting your reinforcement, or in case of an isolated. Okay, this is your reinforcement, and this is how the reinforcement will be looking like. Okay, so that's another software where you can use for your design of a foundation. Anyhow, this is only to illustrate for you that you can do only the soil parameters are assumed. Other than the soil parameters, all of them are given in the question. Okay, other than the cover, and then the cover and yeah, the cover is only you have assumed from the beginning, but other than that, only soil parameters you need to input. Okay, there are other software, like for example, if we use TEDS. Okay, we can go for new, and then we can choose foundation from here. After foundation, we can choose bad footing analysis and design to BS 8110. Then calculate. Okay, it will ask you how many number of columns. Length is 3000, width is 3000, depth 550, density of concrete is 24, 300, no eccentricity. When it comes to surcharge, there is no surcharge, so I kept it as 0. Soil details. The most important thing here, if you want to have a backfill, then you need to control the depth of soil over the foundation, and you need to control the density. For example, if this is 1800, this is 18, you need to input these parameters. Okay, and then the most important thing for you is here, which is the safe bearing capacity, which is 170. Okay, and you can choose the type of soil as well, granular or cohesive. Loading, how much is the loading in the column number 1? So we have 150, and we have 300 as an imposed load. Okay, we don't have horizontal loads, we don't have moments. Okay. Clicking on OK, next. You can see that this is the ultimate pressure now. Okay. Or this is the service pressure according to the software. So it fails because of once again, because of the backfill that we have kept. So 1.151. If we try to go and change, for example, keeping the depth of the soil over the foundation to be 0, then going to next, you can see that it's lesser than 170 now. Okay, once again, the backfill will control. So now you can see it will ask you for further things. So for example, grade of concrete is 35. Now you don't have 500 here, you don't have 460. But if you have used 500, then it's fine. Did I explain for you 460 and 500 in terms of factor of safety? Did I explain 1.01 and 1.115? No, I didn't. Okay, so I didn't explain for you. Okay. Now when it comes to VS Code, there are 2 grades normally which are used. Okay, there are 2 grades which are used. If we go here, the BS, which is 1997. Okay, VS 1997, which is this one, using BS 1997. Okay, is using a grade of steel of 460. Okay, BS 8110 version of 1997 says for you 460, and it says for you as well how much or what is the minimum grade to be used. For example, for reinforced concrete, the lowest grade to be used is C15 in case of a lightweight concrete or a lightweight aggregate. So if we are talking about lightweight aggregate, the minimum is C15. If we are talking about normal weight concrete, then it's going to be C25. If we are talking about a BCC, if we are talking about a BCC, then it says for you it's going to be C10. Okay. So you need to know these details from where they are coming. Anyhow, now if we return back to check the factor of safety for the steel, you can check that according to 1997, the factor of safety for the steel is 1.05. What does it mean? It means that when we order steel, the grade of steel that we are ordering is 460, but it's impossible to get all the bars of the same reinforcement, I mean of the same strength. You might be getting something 460, something lesser than that. So you need to give certain flexibility in terms of the value. So the code has told you if you're using 460, then there is a flexibility of 5%, which is 1.05. So now the value is 483. So the code says for you, any bar which is more than 483 to 460 is acceptable. Okay, so once again, the grade is 460, but we are allowing 1.05. Now a person is asking from where did you get this 1.05 or where they are included in the equations. I will say now you are using, if you remember, M or AS is equal to M divided by 0.95. From where the 0.95 came, it came from 1.05 only. Okay, so we are allowing 5%. So instead of taking 100% of the steel strength, we are taking 95% of the steel strength, which is 0.95. That's why we multiply 0.95 into FY. That's in case of 1997. Okay. In case of the new version, which came in 2004, okay, you can see that the grade of steel now is changing to 500. Now in the construction market, we don't have 460 anymore. We have 500 in the construction market. Okay, so in the market we don't have 460. Yeah, I remember I explained it, but since you said I didn't explain it, so I'm explaining it once again. Okay, so in case of 500, we are using 1.15. Okay, it says 460. Whenever you are using 460, you can use 1.05. Whenever you are using 500, then you should be using 1.15 according to the table here. Okay, according to the table here, we are using 1.15. So once again, if it's 500, then we are allowing 15%. Okay, so it will give you around 434. Now the first one is 434, the second one is 437 or 38. So both of them are very close. So whether you have used for your design 460 or you have used for your design 500, as long as the factor of safeties are used correctly, then both of them will give you almost the same answer. Okay. So returning back to TEDS, so 500 will not matter. Cover is 50. Factor of safeties you need to input directly here by the code 1.6 and 1.4 next. Okay, now if you see here, it says for you the top reinforcement diameter is 12. We don't require top bars, that's why it's 0. For the bottom, It says for you diameter used is 12. How many bars? 15. 15 will give you 200 spacing center to center. Now it says for you the required reinforcement is 3,582 for the whole width or for the whole length of the foundation. You are providing only 1,696. Required is 3,500. Provided is 1,696. So what we can do, first thing, we can increase the bar. For example, I can go for 14. Now you can see if I change to 14, this will change. So you can see now it's becoming to be 2,300. Let us keep it to be 16. So now we have 3,500. We have 3,000 provided. We can increase the number of bars and we can keep it to be 20. Now see what will happen to the spacing. Of course, if you increase the number of bars, the spacing will be lesser. So you can see the spacing is now becoming to be 150. Okay. So required is 3,500. Provided is 4,000. If you want to be a little bit safer, you can go here. So it says for you 1,000. The spacing is 175. Required is 3,500. Provided is 3,600. So we are safe. Now going for reinforcement in Y once again. Required is 3,700. 3,700. And then provided 1,696. So it's better always to keep the same reinforcement in case of an isolated model. So we are going to go for 16, and then we are going to go for 20 bars. Once again, the spacing is going to be 150 and 150. Now it's passing here. We'll go to next. You can check that everything is passed. And this is your design of an isolated foundation where they have taken everything into account. Okay. So how to calculate the moment, whether there is eccentricity, there is no eccentricity, and you can see. I don't know that it's possible to check. Okay. So, if you can see, you can see that they are using WL square over 2. WL square over 2. In case of any other moments, they are using the different equations. Okay. But anyhow, you see, we are using the same equation where K is equal to M divided by FCUBD square. Dx is equal to D capital minus concrete cover minus diameter over 2. AS is required to M divided by 0.87, from where the 0.87 came. 0.87 came from 1 divided by 1.15. Is 0.87 because we are using 500 as grade. Okay. So everything as whatever you have studied, 13%. Everything is the same. VC is 0.79 multiplied by 100 AS divided by BD to the power of 1/3 multiplied by 400 divided by D to the power of 1/4, and it goes on. Okay, and you can see now everything is designed. This is your reinforcement in one direction. This is the reinforcement in the other direction, and you can go and take this one if you want. Okay. So design of a footing. Designed by Ahmed, today's date, checked by Ahmed, and then approved by Ahmed. So you can write your names. This is going to be beneficial for those who are having projects. And then you can go to send for TEDs for all. And you can see now, you can see that everything has been brought to the Word for you. Okay, so this is another alternative. Another software you might be using. Another software you might be using is Robot Structural Analysis. In which directly we can go for new project, and then we can go directly for RC element design. From the options here, we have beam, column, foundation. So we'll go for the foundation. So it has been given certain values here, certain cross-section direct. If you want to change them, you can go, you can change them from here. No, for your assignment, you need to use manual. Okay, so we need to keep A and B. For your assignment, you need to practice for your final exam. So 0.3, 0.3. And then we'll keep these. We'll keep H1, which is the depth now. We'll keep it as 0.55. H2 or H4. H4 is representing the BCC layer. So we can click on apply. After doing that, of course, you can go and change the condition, but normally it's going to be very severe for a foundation. We will go for the loading. It will ask us what type of loading, so it's dead load. Just input it as 1050. Second one is going to be as a live load, and the value is 300. Now, of course, there are different loading cases where moments is there, moment in one direction, moment in two directions. And then we'll go for the stresses. The most important thing, going for the allowable. We're going for allowable. Now, this is not a unit that we normally understand. This is not a unit that normally we understand for safe bearing capacity. So I'll just go here, job preferences. We'll go for units and formats. For forces, I'll tell stresses. I want the stresses to be shown in Newton per, let us say, kilonewton per meter square. Okay, kilonewton per meter square. And you can go here. Now you can see that it's going to be in kilopascal. It's up to you to choose whatever you feel correct. All are good. Okay. And then we are calculating. So you can see directly. The robot has manually. It did not say for you using a software. The assignment is manual only. Okay. So you can see that the software has automatically. Okay. The software has automatically changed the dimension for U3 according to the safe bearing capacity. Okay. And this is going to be your pressure, service pressure. This is going to be your service pressure, and you can see that this is the ultimate load according to the software. I don't remember how much we have got the loading. How much was the ultimate loading? So the ultimate loading in our case is 1950, and then we have 1485. So here 1471 approximately. So the software will be calculating the exact value of the self weight rather than 10%. Okay, and then you can go for the reinforcement. This is your reinforcement, how it will look like. Okay, this is my reinforcement. You can change the shape if you want. Okay, then we can go for shapes. We can have hooks. 90 degrees, let's say. 90 degrees. Okay, you can put the length of the hook. You can put it and increase it. There is nothing called complete analysis accuracy. There is something called user friendly, and which one is going to be preferred for each and every person. For me, both of them are good. Okay, so this is your foundation with the reinforcement. Okay, this is your foundation with the reinforcement, where you can see that you are having 52 bars in both directions, so 26 in one, 26 in the other direction, and then we have the starter bars of the column to be. Okay, Now, of course, you can go and change the grade of concrete whenever you require. For example, C35, which diameter to be used, which diameter not to be used. Okay. So this is only a sample. This is only a sample to show you how you can use software in order to do the design of a foundation. Since I have showed you for the slabs using Excel and I think Tekla, Tekla TEDs we have that. So I'm showing you how to do it in different software for the foundation. Now returning back to our lecture. Returning back to our lecture, where we are going directly to column design. Okay, where we are going directly to the column design. Now there is one problem that we didn't solve here, which is related to function share. I have given you a hint where maybe it will become closer for you to answer the question. Okay, although the question is not hard, but it came in one of the final examination. Okay. Now if you see here, the question is asking you to calculate the maximum loading, taking into account that you should not exceed the ultimate shear stress. So we are going to use mainly the equation of V equal to shear force divided by cut area, if you remember. Okay. Now where we need to know how much is V. Okay, we need to know how much is your V, and then we need to know the cut area. Now for cut area, it's going to be somehow easy where you need to have it as B to D, where D has been given here, and B you can take the width of the foundation. If the width has not been given, you can assume it to be 1 always. Okay, so these two are available. Now for you, the remaining thing, when I say maximum load, it's the same thing when I say it's a shear force. Okay, so the thing which is only pending for me is the shear stress. Now for you to calculate shear stress, there are two scenarios. Scenario number one, where we are talking about without links, okay, or with links. Now we said if your VC is more than V, then you don't require any shear. Okay? If your VC is more than your V, then you don't require any shear. So you can go and substitute this VC here. The worst scenario is where VC is equal to V. The worst scenario, in case of no links, VC will be equal to V. Okay? So VC, you can go and calculate it using the equation in the code. If we open our code, okay, and we go to the chapter of shear. We will go for shear reinforcement requirements. This is the design shear stress. Okay. And this is your VC. You can get the equation from here, or you can get the equation from here as well. It's written here. So everything is given. You have 0.79, gamma M is known to be 1.25, 100 AS. AS has been given in the question. If you return back to the question, you can see that you have 20 mm bars with 200 mm spacing. So 20 mm bars, 200 spacing. So you can go here, check into according to 20 mm bars, 200 mm spacing. You should be having a value of 1,570. So AS is available, B is available, D is available, so you can calculate VC. If you calculated VC, and you know your cut area, you will be able to calculate your shear force. Okay. Now going to the column. Going to the column. Okay, I think most of you know already the function of the column. Okay, knows the function of the column, that the column is to transfer the loads from the upper levels to the foundation. Okay, that's the function of the column. But when it comes to deciding, okay, when it comes to deciding whether this element is considered to be a column or considered to be a wall, then there is a clear-cut criteria given by the code. Says if you are talking about a certain element which is having B as width, D in terms of depth, this is acting now to be a column, this is acting to be a wall. You can see the main difference between these two, that the ratio of D to B, the ratio of D to B is very huge in case of a wall. In case of a column, they are not huge. Not the height. Height might be the same, but once again, the ratio between the depth to the width of the section is smaller in case of a column compared to a wall. And how much smaller, the code has specified. Now the code says for you, if your D is lesser than or equal to 4 times of P, then it's a column. If it's more than that, then it's considered to be a wall. So for example, if we are having a cross section, of a column, a cross section of a column that is 200 to 750, then this is considered to be a column because your 750 is lesser than 4 times of 200. 4 times of 200 is 800. So if this one is more than 800, second scenario, if this is 200 and this is becoming now 900, then this is a column and this is considered to be a wall, whether it's a bearing wall or shear wall. But anyhow, if it's 4 times more, if it's 4 times more than the width, then it's considered to be a wall rather than a column. Okay, walls can be designed only for vertical loading, only to take the dead load and live load, and we call them to be bearing walls, or they are intended to take the lateral loading, like in case of a wind or seismic, and we call them normally as shear wall. Okay, so this is clear, I think, right? This is clear, and this can be found as well. This can be found in the code facts or the actual code. So if we go available in samples and abbreviation, it might be in the column. Okay. The actual code. Because I didn't get. I'm searching. So it's not available here, it seems. Okay, it's not available here, it seems. It's available in the code if you go for 1997. The actual year. Yes, of course. There's a difference. So if we go to the code, you can see here in terms of definitions, different definitions are there for each and everything. So So it says for you wall, a vertical load bearing member whose length exceeds 4 times its thickness. Okay, so this is the definition in terms of the BS code. In other codes, it's different. Okay, in other codes, the definition normally for this one is the same, but the cylinderness is different. We'll see it later. Okay. Now, what are the loadings? We have none, right? When it came to the slab, we have none. When it came to the slab, still my voice is not clear. My voice is not clear now. Clear. Okay. So we have talked in the foundation. In the foundation, we have talked about the different loadings coming on a foundation. And if you remember, we said the loading coming from the top, we said backfilling, we said start charge, we said the self weight, if you remember. So now when it comes to the column, we need to understand what are the loading coming on a column. Now, for example, if we have taken column number C, now you can see column number C is carrying certain part of beam number 1 and certain part of beam number 2. So if I draw beam number 1, so this is my beam number 1. Now this is a reaction here. This is a reaction here. And then of course there is a loading, whatever is the shape of the loading, whether it's a UDL or a trapezoidal, whatever is the shape. You will see that certain loading will go as a reaction here, and the other half is going to go here. Okay. In the other scenario as well, in the other scenario for beam number 2, there is a column here, there is a column here. So once again, half of the loading will go here, and the other half will go here. In case of a simple, okay, not a continuous. In case of a continuous, it's not going to be perfect half. So half for the right side, half of the left side. Now this is a position. This is a position where column number 1 is acting, or C. Now this C will be taking what? This C will be taking the reaction from B1 plus reaction from B2 plus the self weight, or whatever we call it as own weight. Okay. So self weight of the column. Okay. So once again, we have reaction coming from beam 1, reaction coming from beam 2. Okay. So this one here, and then we have the self weight of the element. This is what's shown as R1, R2, and then the self weight. Okay. So in this scenario, your N is going to be R1 plus R2 plus self weight of the column. Now going for, let me just do this. Now it says for you here that the self weight can be calculated if you have the dimension of the column, if you have the dimension and the height of the column. If you have the dimension and the height of the column, you can calculate it directly by using the volume to get the unit weight. Okay. You can calculate the self weight of the foundation as area multiplied by the height, which is the volume. So the volume multiplied by unit weight will give you the self weight of the column. If it's not given, and you need to estimate the load, the self weight, then you can take 10% once again, the same as whatever we have done with the foundation. Okay. Now going here, there is something called braced and unbraced. And I'm assuming that you have studied. I'm assuming that you have studied column chapter in design of structures 1, right? So you should know all of these basic things that they have mentioned. Did you study the design of columns? Okay. So you should be able to bear these particular basics because you have studied them. Okay. So we have something called braced and we have something called unbraced. Okay, we have things called braced and things which are called unbraced. Now if you see here, we have two scenarios. We have the scenario of braced and scenario which is unbraced. Now this is what's unbraced and this is braced. Okay. Now if you see these x's, the blue x's are representing positions of columns. Okay, these x's are representing positions of columns. Okay. Now if you can see here there are no barriers. There are no barriers protecting my building. Okay. In terms of lateral loading. Now of course this will be taking the gravity load and this will be taking the gravity load. Dead and live load directly will be taken. But when we talk about braced and unbraced now, we are referring to whether the column is to be designed to take that particular lateral loading or not. Now in case of picture number 1 or the left side, you will see that we don't have walls. We don't have shear walls. The right side, you will see that we have red walls, red shear walls, or shear walls which are in red. Can you see the difference between the first one and the second one? First one only columns. Second one we have columns and walls. Okay. Now in both scenarios, columns will be taking the gravity loads which are going with the gravity, which are dead and live. Okay. In the left side, there is nothing taking the horizontal loads except for the columns. Now the second scenario, the horizontal loads will be taken by the shear walls, by the stronger parts, which are the shear walls. Okay. So once again, in case of braced, the column mainly is designed for gravity loads. In case of unbraced, the column is designed for both gravity and lateral loading. Why? In case of braced, there are elements which are thicker. They are supposed to be acting as resistance to lateral loading. In case of unbraced, which is the left side, there is nothing helping the column from taking the lateral loading, so you need to design it to take the lateral loading. Okay. Are we clear about the concept of braced and unbraced? Are we clear about the concept of braced and unbraced?
Mister, can you please repeat the unbraced again?
Unbraced means the column is to be designed for both gravity and lateral loading. Unbraced, what's the meaning of braced? Okay, what's the meaning of braced? Bracing, you have studied bracing, right? Do you know what's the meaning of bracing? Bracing is like horizontal resistance. Normally we use horizontal resistant elements. We call them as bracing. I think you should have studied it in steel design. Okay, so bracings. Now you can see in terms of horizontal, the column is not protected by any other member. So this column is going to move or sway. Now in order for me to protect the column from failing, you need to design it for that lateral loading. Okay. When it comes to the right side, there are elements who are stopping that lateral loading from causing the building to sway. Okay. If you remember the example, able to withstand the horizontal forces. You will design, it's not only withstand, but you will design them for workforce in construction. I didn't get you there. What do you mean by for workforces in construction? What about them? No. No. Bracings are normally horizontal elements which are going to stop you or restrain you from moving in the horizontal direction. That is your bracings. And you can see here, this is an example where you can see we have columns and we have shear wall. So since shear wall is there, then these columns are going to be designed for gravity loads mainly. And when it comes to real construction, you will see that if your building is three stories or lower or lesser, it means that normally the lateral loading, whether it's wind or earthquake, the effect of these two loadings are not that much. Okay. So in this scenario, the column is not having a major load in case of lateral loading, so we don't need to take it into account. But if we are designing for more than 3 stories, normally the municipality will force you to have a lift. Now the lift is consisting of shear walls. Okay. Shear walls joined together, and we called it to be a core wall, if you remember. Now in case of a core wall is a very heavy element. It's a full concrete wall, a very heavy element which will stop your building from moving, or it will restrain your building. Let's say not stop, but it will restrain, it will reduce the movement in case of any lateral loading of wind and earthquake, because it's very heavy. The same example of the paper I have given you, I think. If I take a paper in front of the AC, you will see that because of the AC, it will move from its position. Now, if you keep something heavy on the top of the paper, you will see that it will not move. So what did I do? I made the building, or I made the system to be a little bit heavier. So when you are presenting that lift in your building, the lift is very huge. It's very it's very heavy. So since it's heavy, it's going to go and restrain you from horizontal movement. The same thing if I have a rock and I want to push it, a rock which is available in the ground, and trying to push it. If the rock is not heavy, then it's very easy for me to apply lateral loading, and then the rock will move. But if the rock is very heavy, you will see that whether you are applying a lateral loading, it will restrain you from moving. Normally core walls normally are for lifts. Other than the lifts, you are using normally shear walls. Okay. But for example, in areas where the geometry let's say is not typical, you might be ending up joining two walls together. If you are joining two walls together, then it's going to be a core wall. Okay. But normally core wall is known to be as a lift. Now the other thing that we are going to tackle is the effect of shortened cylinder. And if you remember, we talked about a lot in the beginning of the semester. We talked about buckling, we talked about bending, we talked about flexural element, we talked about axial element, and we said, if you remember, cylinder bars will not buckle. A lot of things we have discussed. So the same concept is applied here. Okay, the same concept applied here. And we said, if you remember, it's not only about length. We said it's not only about length, but about the cross section as well. Okay. We said even if I have a long element, but the thickness of the element is huge, it will not buckle. Okay. So you can see here the code has taken LEX over H and LEY over B. Okay. Which is representing effective length. H is representing thickness or the depth. B is representing the width. LEY is representing effective length in terms of y-axis. And I think you have studied in your design of structures one LEX and LEY, so I'll not go a lot in LEX and LEY, but what you need to know that, let's say let's say that this is the column. Okay, this is my column. And then the height of the column is, let's say, 3.5. Okay. This is what we call as L naught. L naught is the total height of the column. Okay, L naught is the total height of the column. Now you will see when this column is going to fail, it will not fail from the top. Okay, it's not going to fail from the top. It is going to fail somewhere here. And this is whatever we call it as. This is whatever we call it as. Not necessary. This is whatever we call it as LE. Okay, this is whatever we call it as LE. Okay. Not necessary points. Okay, so if you see, if this is a fixed, this is a fixed. Okay, and if you try to rotate it, then you will see it like a fixed beam. And in case of fixed beam, the deflection here is equal to 0. Deflection here is equal to 0, and you will see that it will deflect in this manner. Okay. Now the same thing for the column, because it's a rotation of the beam here and here. And then you will see this one. Now this is acting as your LE. Now in case of, for example, in case of a pinch support with a fixed support, and then the same thing, pinch support, fixed support, you can say that here it will deflect directly, and then here there is a portion because of the fixity. So you will see that now this is your LE. Okay. Not necessary. Okay. So this is your LE. That's whatever we call it as theoretically. Okay. That's whatever values you are showing now, 0.7, 0.85 at the theoretical, not the designed one. Okay, not the design one. So you can see that this LE is bigger than this LE. Anyhow, how would you calculate this LE? How would you calculate them? You will calculate them based on these particular tables, and I believe you have studied these tables, right? Have you studied these tables? Have you seen these tables previously? In your design of structures one, have you seen these tables? No. Okay. So if you see the equation says for you LE equal to beta multiplied by L naught, where L naught is the total length, LE is the effective, we need to multiply it by a certain factor of safety. Or certain factor, let's say, not factor of safety, but certain factor. Now you can see here we have 1, 2, 3, 1, 2, 3. What do they mean? 1 is representing fixed. So if the end condition is fixed, okay, if the end condition at the top is fixed, so top condition is fixed, bottom condition is fixed, the design coefficient is 0.75, not 0.7. Okay. And it says for you number 2. So number 1 is fixed, number 2 is pinned, number 3 is simple or roller. Okay. So fixed, let's say partially fixed, simple, fixed, partially fixed, simple. Now if it's simple at the top and simple at the bottom, you will see the value is going to be 1. Okay. If it's somehow fixed, and then pinned in the other side, you can choose, for example, 1 and 3 or 1 and 2, depending on how fixed is it. Okay. And there are conditions which will tell you in what basis you are going to take it as 1, in which basis you are going to take it as 2, and which basis is going to be taken as 3, according to the dimension of the column and dimension of the beam. Okay. According to these two dimensions, you are going to decide which cases Number 4 is representing free. So number 1 is fixed, number 2 is partially fixed, number 3 is simple, number 4 is a free end. Okay, a free end means like a retaining wall. At the bottom, you can see at the bottom there is no number 4. At the bottom there is no number 4, but at the top there is 4. So in case of, for example, in case of a retaining wall, you will see that it's fixed from the bottom, but from the top it's free. Okay, so that's case number 4. Not everyone will represent. The things as whatever we want. And when for example, if I say for you simple end and free end, and I say for you partially fixed, the second question you will be asking yourself, to what extent is partially fixed and what's the meaning of partially fixed? So a lot of questions will be arising. So rather than doing it in that way, they have classified it 1, 2, 3, and 4, and they have given you what is the meaning of 1, what is the meaning of 2, what's the meaning of 3, and what's the meaning of 4. But in terms of explaining it for the student, it is the way how I told you. Okay. So once again, if you go to your now, I have not explained it here because I was assuming that you have studied it in design structure zone, which is a basic part. But anyhow, you can go here. Let us see. Okay, so these are the values. Okay, these are the values. These are the values or the tables that have been shown. It says for you, the end of the column is connected to the beams directly on either side, which are at least as deep as the overall dimension of the column. So if you are talking that the dimension of the beam to the dimension of the column are at least equal, or the beam is equal to the column or more, then it's going to be a fixed. Okay. So you didn't design column. You didn't design column and design what? So you didn't do actual design of a column? Then that's a big problem. Okay, anyhow, the conditions of 1, 2, 3, and 4 are shown here. Okay, are shown here. Anyhow, normally if you're using a software, mainly, these are going to be shown by the software, but for your just understanding, I'll see if there is time for me to go and explain for the condition one by one, but there are things which are more important than the condition. Okay. Anyhow, as I told you, condition number 1, 2, 3, and 4. 1 is representing fixed, second is partially fixed, third is simple, and the last one, which is number 4, referring to a free. Okay. So the code says for you, if your LEX over H is lesser than 15 and your LEY over B is lesser than 15, then your column should be considered as short. Okay. Your column should be considered as short. So since you didn't study it, next class I'll try to give you extra problems on how to find the value of LE. But I'll try not to spare a lot of time because a lot of things are more important to come. Okay. Normally these coefficients are calculated by the software, although you should know them. Okay, so once again, LEX over H is lesser than 15 and LEY over B is lesser than 15, then the column is considered to be short. Now, certain students in the project, they will bring the coefficient to be 12. Now, the Indian code says for you, the Indian code says for you 12. The VS code says for you 15. So you need to be careful which value you are using. Okay. Now, if we return to our extracts, before going to the bi-axial, so see here, shorten cylinder column. It says for you a column may be considered as short when both the ratios LEX over H and LEY over B are less than 15 in case of braced and 10 in case of unbraced. So 10 for unbraced, 15 for braced. It should otherwise be considered as okay. Now my question says for you. So for example, if we are here, we have got LEX. Next class we are going to learn, because I need to bring for you the problem here to illustrate LEX and LE1. Okay. Now if we are having LEX here, okay. So for example, if we are having a beam here, if I'm trying to draw that there is a beam here, okay. Okay, there is a beam in one direction only, not in both directions. Okay. Or let's say here and here. Okay. Now you can see in this direction, this is the length. This direction, the length of the column will be stopping here because there is a restraint. So it means you are telling me that there is a column, there is a beam, and there is a column. Okay. So your value of LE will be affected here because of the restraint. You cannot see the screen, others? Others, are you seeing the screen? Okay. Okay. This is in this direction. Now in the other direction, which is here, in this direction, can you see that there is a beam in this direction? Is there any beam? No. Okay. So the height here is going to be different from the height of the previous case. So that's why we calculate sometimes for LEX and we calculate for LEY, because it's not necessary that your LX and your LY are the same. Okay, it's not necessary that your LX, LEX, and LEY are the same, and we'll see in the next class with a real example on how to do that. Okay. Now, if according to my calculation, LEX is, let's say, 10, and LEY over B is, let's say, 12. Now this is considered to be what, cylinder or short? LEX over H 10 in case of braced, because we are designing braced. Okay, so in case of LEX over H and LEY over B, both of them are lesser than 15. Both of them are lesser than 15. Okay, so we are having it to be short. Second scenario, if your LEX over H, is 16 and LEY over B is 15. Short or cylinder? Cylinder. Once again, if the value is 15, okay, there is a big fight if the value is 15, whether to be cylinder or short. But if you are taking literally whatever the code is saying, then 15 goes for cylinder. Okay, 15 goes for cylinder. Now, what if what if your LEX over H is 10, your LEY over B is, for example, 17. Like you can see in this scenario, your L in one direction is big and in the other direction is small. And you ended up having LEX over H to be 10 and LEY over B to be 17. Now what will you do in this scenario? Is it short? Is it cylinder? Maybe take the more critical cylinder high. Okay. Now in this scenario, this particular portion, which is getting you 10, is going to be designed as short. And this particular portion, which is giving you 17, this is going to be designed as cylinder. Okay. No, it's not going to be taken as a cylinder column. It's not going to be taken neither cylinder column nor short column. The side which is cylinder should be designed as cylinder. The side which is short should be designed as short side. And we'll try to see a problem where this is going to be happening. Okay, although I didn't put it in my scope because of I thought that you have studied in design one. Okay, no problem. I'll try to cover it next class. This is basic information. I think you know it from design one. I'll not explain it further. The column can be of many shapes, not only the ones shown here. It can be square, it can be rectangle, it can be a circle, it can be I shape, it can be L shape, it can be T shape. A lot of shapes over the columns. Okay, a lot of shapes over the columns. But what you need to know is the minimum number of bars. Now, what you need to understand, the code says for you the minimum number of bars for a column for a certain conditions are 4 for rectangle, 4 for square, and then 6 for a circle. Why 4 for the square? Because you have 4 angles or 4 sides. Okay, so we need to, in order for me to maintain the shape, I need to have a minimum of 4 bars. The same thing goes for a rectangle. I need to have at least 4 bars in each and every corner to maintain the shape of a rectangle. For a circle, I cannot put 4 because your shape will not still be maintained. Okay, you need to place at least 6 bars to take the shape of the circle. Are we clear? Okay, so once again, the code says for you the minimum number of bars in case of a rectangle or square is 4. In case of a circle, it's 6. Even if you require, even the AS required was only requiring you for 1 bar, the minimum says to be 4, then you need to supply 4. You cannot maintain the shape of the square if you are having only 1 bar. It will never be a square or a rectangle in reality because of 1 bar. At least the 1 bar is maintaining the shape. Okay. Now where we can find that in the code, you can see here. See, now you can see here for braced and unbraced as well. It says a column may be considered braced in a given plane if lateral stability to a structure as a whole is provided by walls or bracings. Okay. So we said if there are elements to take the lateral loading or which are ensuring the lateral stability like walls or bracings, then it's considered to be braced. If not, then considered to be unbraced. Minimum number of bars for a rectangular column is 4, for a circle is going to be 6. Now, of course, square is a special form of a rectangle. So square is 4, rectangle is 4, circular is 6. And the minimum size of bar to be used according to the code is 12 millimeter. So according to the code, the minimum diameter to be used is 12. I think we are going to start here tomorrow, or the day after tomorrow. We are going to take the different type of loading, and we are going to hopefully solve one problem at least. Okay. Any questions you have for today's lecture? I'll not start a newer part which is for loading because I'll not finish in 4 minutes. Okay. Any questions that you have? Any questions that you have? Because we have finished the lecture. If you don't have any question, then you are free to leave. Once again, the assignment